Okay, this is lesson 7 of Calc A review. Today we'll talk about Extrema. Let's go down to the first real slide here. Start with some definitions. Increasing and decreasing. We say a function is increasing on an interval if f of x1 is less than f of x2 anytime x1 is less than x2, basically meaning as you move to the right on the number line, x values are getting bigger, the y values are also getting bigger. Decreasing would be the opposite of that. Function values or y values get smaller as x gets bigger. Increasing and decreasing are terms that describe intervals, characteristics of an interval. You might describe a function as increasing from 0 to 2, but you would never say a function is increasing at a single value like x equals 1. Increasing and decreasing is a description of what's happening at locations relative to locations around it. You need to include an interval of locations. Also, quick note, I'm using brackets here. It is considered acceptable to also use parentheses when describing intervals of increasing and decreasing. All right, if a function is continuous and also differentiable within a certain interval, well, if f prime is greater than 0, meaning you have positive derivatives at every point of the integral, then you know it's increasing. Likewise, if the derivative is negative at every point in an interval, you're decreasing. This is why we often justify increasing and decreasing by looking at derivatives of functions. Speed. Speed we know to be the absolute value of velocity. It doesn't include a direction. That means speed is always greater than or equal to 0. A question that has come up frequently on the AP test: can we determine when speed of some object is increasing versus when speed is decreasing? The quick check for that is as follows. Speed increases if both velocity and acceleration are positive, or also if velocity and acceleration are both negative. Because in those cases, if you were to graph speed, or even if you were to graph velocity, you're moving away from the horizontal axis. I mean, speed is increasing. So long story short, speed increases when v and a have the same sign. Speed decreases if v and a have opposite signs. And then just for reference, here's a velocity graph and the corresponding speed graph that kind of confirms that. Down here especially, this is where, this is where velocity is negative and acceleration is also negative. That corresponds to places where speed is, in fact, increasing. Let's do an example. 7.1, we have the position of some particle described by a function. It's also worth noting we have an interval of time values that we're looking at. Part A wants you to find a velocity function, we'll call it v, and acceleration, we'll call it a. And of course, the easy way to do that is to differentiate position to get yourself a velocity. Make sure you think about chain rule as you're doing that. And then, of course, we differentiate that result to get to acceleration. We're using chain rule again in there as well. All right, so now we've got some tools that we will presumably use in the other parts of this example. Part B says, find the times when velocity is decreasing. Justify. This is huge. This is important. Probably worth, more points on a free response question than the actual final answer is your justification. You have to explain using calculus reasoning why this is occurring, okay? So typically the way we do that, we say that a function, in this case velocity, is decreasing when its derivative is negative. In this context, that would be acceleration being less than 0. So we want to find these locations where acceleration is less than 0. We'll probably start by taking the acceleration equation and setting it equal to 0. Okay, if we can do that, that will give us cut points on a number line, and then we can investigate on either side of those cut points what is the behavior of acceleration. So we set this guy equal to 0. And of course, this is only going to equal 0 if the cosine expression is equal to 0. So now we need to think about what values of t would make this cosine expression equal to 0. And really what I want to do is think about what does pi t over 2, this angle plugged in, what does that have to equal? And now we think back to trig. What are the various locations where cosine goes 0? That would be pi over 2, 3 pi over 2, 5 pi over 2, and of course there's many more that follow. That means we need pi t over 2 to be equal to one of these values. And once you write that out as an equation, really we're solving multiple equations at once, but if I divide everything by pi over 2, I actually get some really nice numbers. But I only want the ones that are between 0 and 4. So I can ignore most of the results and focus on t of 1 and 3. So now I turn to my number line. All right, you'll notice I put the endpoints of our original t interval down here as well. I'm also going to put these zeros that we just found. And then it's up to you to pick values in between 0 and 1, in between 1 and 3, in between 3 and 4. Plug some values back into this equation just to confirm, am I getting positive or negative results? Because these zeros we found would be the only possible locations that acceleration might be switching signs. So if even a single value between 0 and 1 gives us a negative acceleration, that means this whole subinterval is negative. All right, so I've picked some values, I've plugged in, I've checked, I found a negative, positive, negative pattern, but we're mostly interested in acceleration being negative. So our answer will report from 0 to 1, from 3 to 4, the interval notation. Part C, find the times when the particle is moving left. Typically in these number line example problems, moving to the left corresponds to a negative velocity, whereas moving to the right would be a positive velocity. So really what this question is asking is, can we figure out the times when velocity is less than 0? And by writing that down in words here, I'm justifying my answer. I'm not just going to give a final answer in interval notation here. I'm going to sort of explain why I'm looking for whichever interval I eventually report. So similar to the previous part, except this time I need to be careful and take my velocity, set that equal to 0. We solve it out a similar way. I want to think about angles where sine is 0, and then I want to set pi t over 2 equal to those angles where sine is 0. Divide all these results by pi over 2. We get t values of 0, 2, 4, and then of course there's others that we disregard. So here's my number line for the velocities. And again, you pick values of t between 0 and 2. Maybe you pick a 1 in there, plug it in over here. Maybe you pick a 3, plug it in over here. Just to confirm what are the signs on those subintervals. Okay, and ultimately we're interested in velocity being negative, so it's the subinterval from 0 to 2. That's my final answer for part C. D, find the times when speed is increasing. We referenced this in the previous slide. Speed increases when A and V have the same sign. I'm writing that down. That counts as my justification of what I'm about to do. Now, the number line is going to get a bit more complicated, but at the same time, there's work that I've already done that I can reuse here. I'm going to take the number line from part B. This was a number line that tells us the signs of acceleration. I'll also take the number line from part C, which gives us information about the signs of velocity. I'm going to try and combine those into a single number line. Any cut point that showed up on either of those number lines should show up here. And that is going to require us to break certain intervals up even more. Acceleration, for example, previously we said it's positive from 1 to 3. You'll notice here, because I now have a 2 on my number line, I'm breaking that up into a positive from 1 to 2, but also a positive from 2 to 3. And I have a similar breakage happening in velocity. Okay. And once I've got that all established, I'm looking for any subinterval where the signs match. And I see from 0 to 1 it's occurring, and also from 2 to 3. So there's my final interval of where speed increases. Example 7.2. This one involves a temperature equation. This is a good reminder that not every single word problem is about velocity and acceleration. So here we have temperature. Again, we have an interval of time. Part A, can we find when the temperature is decreasing? Now, it doesn't say to justify, but I am going to still kind of do that here. So that's my first line of thought process here. T, capital T for temperature, T of T decreases when capital T prime is negative or less than 0. Okay, so for that reason, I'm going to look at capital T prime. Can easily apply derivative shortcuts. And as soon as I get this result, I set it equal to 0. That's going to help me get cut points for a number line. Interestingly, the only 0 here coincides with one of the bounds of our interval. So that means there is no sign change happening between 0 and 20 for this T prime. Either this entire interval is positive or it's all negative. You can plug in any number you want between 0 and 20 right back in here to determine what we want. Turns out it's negative. So we can say T must have been decreasing from 0 to 20. If you had parentheses here instead of brackets, that would be considered fine. Part B, let's find a T prime of 10. That's pretty easy to do. That just means plug a 10 in for little t into our derivative here. So that's quick and easy. It comes out to be negative 15 over 2. The harder part is right here. This is a very common AP free response question. Using correct units, explain what that means. And you do want to give a complete sentence, as much detail as you can. Here it means at the 10-minute mark, hence T equaling 10, this object's temperature is decreasing at 7.5 degrees Celsius per minute. Okay, 7.5 being the same as 15 over 2. The fact that I see a negative sign is why I put decreasing. And of course, the units would be original degrees Celsius per minute. Some of you might be tempted to say something like this. You might say the object's rate of change is negative 15 over 2. That's not considered as good of an answer. Instead of just saying negative 15 over 2, we want to use a word that kind of communicates what the negative sign's meaning is. So this is a better answer. That takes us to part C. Determine which statement is true, justify your answer. I believe the question writer intended for one of these to be true, but over the years, I've realized that there's kind of an ambiguity here, and for that reason, there's a couple different statements that I would be willing to accept depending on if you justified appropriately. Okay, what's tricky here and what also leads to the ambiguity is the idea of something not just decreasing or increasing, but decreasing at an increasing rate or increasing at a decreasing rate. When you see a phrase like that, it's often pointing to a second derivative, okay? So now I want to look at a rate of change of a rate of change. Yes, if a derivative is negative, an object's value is decreasing, but the rate at which that decrease is happening requires yet another derivative. So for that reason, off to the side here, I have calculated capital T double prime. It's a pretty easy derivative, it comes out to be a constant, which is nice in that it tells us the second derivative is just always positive. Okay. Keep in mind, we already figured out that the first derivative is always negative from 0 to 20. So because the first derivative is negative, we have to say the temperature is decreasing. All right. So the answer has to be choice 1 or 2. But like I mentioned earlier, I could accept either of those depending on your interpretation. Here I have 2 different possible answers that I think both could be valid. You could say from 0 to 20, temperature decreases at an increasing rate, and your justification would be T prime is negative, but the T double prime is positive. That suggests that second derivative positive rate increasing at or decreasing at an increasing rate, I should say. Okay, well, that's kind of weird because the initial, the first derivative is negative. So if you were to look at the temperature, it's like the change of the temperature is actually slowing down, which is why I would also accept this answer. You could make an argument that it's decreasing at a decreasing rate because, again, first derivative is negative, but second derivative having an opposite signs means its temperature is decreasing less dramatically as T increases. I wouldn't get too worried about that discrepancy. I've never seen a poorly worded or ambiguous question like this show up on the actual AP test. So it's just interesting to look at a couple different thought processes that I think are both valid arguments. All right, now we are on to the main topic of this video, Extrema. I'm talking about maxes and mins, different classifications of maxes and mins. So here's what we need to know. At a particular location like x equals c, you have a absolute or global max if f of c is greater than or equal to all the other y values in the entire domain. So it's either the highest point or it's tied for being the highest point. Absolute global min would be the opposite. It's the lowest or equally low as the lowest point. But lots of functions go up and down many times, so there may be other relative or local extrema. Relative or local max, if f of c is greater than or equal to f of x in some interval containing c, or in like a small neighborhood around a certain point. Is it the highest point in an interval that you could point to around it? We call it a local max. Absolute extrema are also considered local extrema. So if you're listing all the locals, you would also list an absolute. Here's a note about Math Excel, which is no longer relevant. We don't use Math Excel anymore, although I don't know off the top of my head how Delta Math treats this, so it's just something to watch out for. Extreme value theorem. If you have a continuous function on an interval, there has to be a highest and lowest point. Maybe there's a tie for one or the other of those, but there has to be at least one absolute max and min. Okay. Example 7.3. Label each graph according to the descriptions provided. Can we find a graph that has a highest point and also a lowest point? And so we rule out this first red graph there because the way it looks like there is no highest point, it appears to keep going up forever. The only one here that actually has a clearly defined highest and lowest point would be the blue one. Lowest point being the vertex of this piece of a parabola, and we do see a closed circle cutting us off at a highest point. Which one has 3 local maxes? 3 local maxes, that of course is choice B. All right, we see left endpoint, right endpoint, and then this discontinuous point here is a max. Continuity is not a requirement for a max. We can still say this point is higher than the points in a neighborhood directly around it. Points directly to the left and right are all lower. C, which one has an absolute min but not an absolute max? That's the red graph for reasons we mentioned a moment ago. As a lowest point, not a highest point. And then interestingly, this green one doesn't have any extrema whatsoever, right? There's a hole at the vertex, which means we get closer and closer and closer to a certain boundary, but we never actually hit it. So you can't speak to a specific finite value and say, this is the lowest one. We can get even lower and lower, even closer to that imaginary cutoff. That's a weird function there. All right, let's keep moving. Derivatives and extrema. At non-endpoint extrema, function's derivative will be either 0 or undefined. Let's not forget about this as an option. However, finding a derivative at 0 or a derivative being undefined doesn't guarantee extrema. That's just a candidate is what we call it. These are places we should investigate further for possible extrema. What we need to find is an actual change in the sign of a derivative at a continuous point on a curve to indicate extrema. There's some vocabulary that goes along with these locations where a derivative is 0 or undefined. 3 different phrases that sound similar and yet are slightly different. Critical point, a defined point, got to be defined, on the interior of a domain where f prime is 0 or undefined. These are your candidates for extrema. Critical number, that word number refers to just the x value of the critical point. Critical value is just the y value. So be real careful. If you're asked to find a critical point and you only give an x coordinate, that's incorrect. If you're asked to give a critical number and you give an x and a y, or a y by itself, that's incorrect. Okay. Let's do an example. F of x given, an interval given. We're going to find some stuff. Setup work, we're probably going to need a derivative here. So I did find the f prime right away. Critical numbers are x values where this derivative is either undefined or 0. This derivative is never undefined. So we just set it equal to 0. We've got our critical numbers. Critical points, we want to now find the y values that correspond to the x values from part A. So just plug those values back into the original function to get y values. You can see I've set up a number line as well off to the right from -3 to 5, and then I'm putting each of those critical numbers in there. And then presumably I picked values in each subinterval to check the signs of f prime. That's going to help us find maxes and mins. So relative max, okay, this would occur when I switch from positive to negative at a location. That does not happen here. So we say there is no relative max from -3 to 5. Relative minima occur when we see a sign change in the derivative from negative to positive. Of course, that happens at x equals 3. But the actual answer is a full ordered pair. I'm not just going to say x equals 3. I'm going to give the point that represents the minimum. Absolute max and absolute min is a slightly different process. It's not enough to just find a sign change, okay? And that's because endpoints could also possibly be your highest or lowest point. So what we often do is we make a table with a column of all the candidates, and that would include critical numbers for x, but also the endpoints. And then the best evidence that you could provide as to where we have an absolute maxes is just find all the y values that correspond to those x's, which is what I've done here. And we clearly see the highest one occurs, in this case, at an endpoint. So -3, 189. You have to show some analysis that proves you've investigated not just critical numbers, but also endpoints on an AP test for absolute max and min. The good news is I don't need to do any further analysis. This table also suffices for us to find an absolute minimum, which I see is occurring when x was equal to 3. All right, we will keep going here. I'm looking at the clock and realizing I might not have time here to finish this video, so there might be a part 1 and a part 2, but I do have a few more minutes. We'll keep going. Example 7.5, more max and min stuff. This time we're looking off of a graph instead of having an equation to work with. Absolute max, okay. There is a highest point, and it's this one right here, 1,3. Open circle over to the right doesn't count. We get closer and closer and closer to a y value of 3 without hitting it. So there's only one absolute max. Absolute minimum, there are two because it's a tie. Okay. Local max, I'm going to list any absolute max that I already listed, but I think that's the only one. There is no other place where our slope is changing from positive to negative, just right here. Well, I mean, technically it is happening here, but you have to have a defined point to call something a max. So this is a special case where we do see a sign change in the derivative, but we don't actually have a max there. Local minimums, there are 1, 2, and then 3 of them. I've listed them all. Where is f prime positive, negative, 0, and undefined? Okay. So we're just, again, looking at the slopes as we travel through. Sometimes it's positive, sometimes it's negative, sometimes it doesn't exist, right? F prime is greater than 0. From 0 to 1, we're moving up, and then also from 2 to 3. Here, you need to use parentheses. We don't want to include those endpoints. Less than 0 from 1 to 2, and again from 3 to 4. I don't see anywhere in this graph where f prime is 0, but I do see 3 places where f prime would be undefined. All right, that's going to have to be a stopping point. There will be a part 2 for this video, so stay tuned for that. Thank you. And again, let me know if you have any questions about what you're seeing. You can ask me in class or via email.